Hello, and welcome to Minitab Statistics for Second Language Research. This is Lesson 4, and in this lesson we're going to learn about regression. We're going to talk about simple regression and multiple regression. This video is based on Chapter 7 of our textbook, A Guide to Doing Statistics in Second Language Research using SPSS and R. As you know, we are translating all the procedures there into Minitab. First, let's define and see what the difference is between correlation and regression. Correlation is a statistical test that measures the strength of a relationship between two variables. The higher the correlation positively or negatively, the stronger the relationship. And this is measured in what we called Pearson's R value. We talked about this in our last video. Now, what is the difference with the regression? A regression is a test used when we have two or more continuous variables, and one is the response variable and one or more are the explanatory variables. The point is to find out how much of the variance in scores the explanatory variables explain or predict future performance on the response variable. And this is measured in terms of what we called R squared. We talked a little bit about this last time, but we will explore this further in this video. For this program, we're going to use French and O'Brien's data from 2008. In this experiment, they were treating French L1 children in an intensive English program, and they were testing phonological memory. And the research question that they had was whether phonological memory can predict ability in learning vocabulary and grammar. So they have a response variable, and this is typically what we put in the y-axis. Notice that the y-axis is going to be the vertical axis, and this is what we call the dependent variable. And in this case, this is the time to grammar. And the explanatory variables, this is what we put in the x-axis. This is what we call the independent variable. He had several. Okay, he had time 1 grammar, intelligence test, language contact, Arabic non-word phonological memory test, English non-word phonological test. What we're going to do first, we're going to review how to do a correlation, and then we're going to run a simple regression with that particular correlation, and then we're going to learn how to run a multiple regression. Now, we already know how to run a correlation. However, last time we didn't talk about the assumptions that we need to check to see whether we have data that are able to be run with a correlation. These are the assumptions for a correlation. 1, the variables should be continuous. In other words, we should have values that change as we measure. Okay, so we cannot have just 2 values, for example, or 3 values. We should have a range of values. The pairs should be related. In other words, if we have a measure, let's say for subject 1, then we should have a second measure for the same subject, and the pairs should be related, should belong to the same subject, to the same entity. 3, we have to check for outliers, and we have to make sure that we don't have extreme outliers. 4, we have to make sure that we have a linear relationship, and we learned how to do this last time. We impose a straight line on our data. If we can do that, then we have a linear relationship. So we're going to do a correlation. We're going to assume that we only have one variable in this case. And the question that we're going to try to answer is whether grammar and English non-word phonological memory are related. So here's the result. We will learn how to do this in Minitab. You already know, but we will review. And we will get a plot like this. Once we get a plot like this, notice that we can superimpose a straight line if it is possible. So here we have a line. Remember that that line is basically going to be the best line that is going to capture the minimal distance from the values to that line. Together with this line that we can impose here, notice that we do have Pearson's R value. Remember that Pearson's R value varies from 0 to 1, and it can go in a positive direction and in a negative direction. Now, the closer we are to value 1, the more correlation we have between the two variables. So in this case, we see that we almost have a 0.8, which is a pretty high correlation. Now, with the same data, we can also run a regression. Now, as you can see, the regression gives us pretty much the same chart, and the only difference is that we have some more information in our graph here. One extra piece of information that we have here is the value for R squared. This is how much our model, this line that we have put there in the middle, can explain of the variation. And in this case, we can see that with this line, we can explain 63.4% of the variation, which is pretty good. Together with this information about R squared, notice that we also have a formula at the top, and I repeat it here at the bottom, and it says that the regression equation is, and it gives us a value for grammar 2. Notice that we can use this equation to predict a value for grammar 2. And in this case, we have 12.73. This is what we call the constant. And we have 0.8884. This is pretty much what is going to give us the value for the slope. And in this case, if we multiply 0.884 by the value of the English non-word, and we add to that the value of the constant, we are going to get the value for grammar 2. Notice that this can be used for data that we already have, and we can also use this equation to predict further data. If we run the assistant with our regression, notice that we're going to get this chart, and here on the right you have again our graph with the regression line. Together with that, we get here a correlation value, and we can see that here the correlation is pretty, it says perfect positive, it's in the green area, and so we can explain about 80% of the correlation. So these two variables are highly correlated, and as we can see in the middle chart on the left, we can also explain the percentage of variation. This is the R squared value. In this case, we have a 63.45% of the variation we can explain with that formula that we discussed before. And at the top, we can see that it tells us the result of the regression test, and it basically says that the relationship between grammar 2 and the English non-word test is statistically significant. In this case, we got a p-value less than 0.05. Today, we're going to learn a little bit about p-values as well. So for the moment, don't worry about that. Notice then that we got a significant result here. So we do have a significant relation between those two variables. And we can predict those values then using that formula that we have there. We also get some further graphs that are important, and you should basically learn what they mean. So here we have the same graph that we had before, but we have some red points. Now, the little squares, the red squares, they mean that we have large residuals. Okay, so these are values that are pretty far away from what we are expecting. And then we have some unusual x's, and in this case we have a couple there. So this is one value, and this is what we call the fitted line plot. Now, if we take that line and then we make it horizontal, this is what we get. And then notice that in this case we do have some extreme values, those marked in red. And what we should do then, these would be outliers in a sense. We should make sure that we got the data right, and then we should go back to our data and check, and then we will learn what to do with outliers later. We also get a regression chart, and also here you see some blue lines. So this blue lines gives you a confidence interval. Okay, so this is like a 95%, and we can see that most of the data that we have pretty much falls within the blue lines. Okay, if we have values that are marked in red and they are outside, we should check and make sure that we have measured correctly. Okay, so now then we are ready, and we're going to go to Minitab, and we're going to run a correlation and a simple regression. Let's go. Okay, so here we are in Minitab, and we have French and O'Brien 2008. I'm going to guide you on how to perform a regression and a correlation, and then you will have a project, but I recommend that you repeat what I do here before you run your project. So here we have pretty much 2, 4, 6 pieces of data. We have grammar 2, grammar 1, intelligence, L2 contact, Arabic non-word, and English non-word. So this is to measure phonological memory. And we have here the subject number, so they can identify the subject, and you can always go back and check your data. Now here we can already check a couple of assumptions. Remember that we have 4 assumptions that we need to check. The first one, we need to check that we have continuous variables, and as you can see here, we pretty much do have continuous values. Okay, so we don't have what we call categorical values, where you would say, you know, yes, no, group 1, group 2, those are categorical. Here we have continuous, we have values all the way. Okay, so we do satisfy the first condition. The second condition was that the pairs have to be related. So in this case, notice that we do have a subject here, and for that subject we have 6 different measures. Okay, so in this case, yes, the data are related. Okay, so we have pairs. Now first we're going to run a correlation, so we're only going to take 2 of these elements, and we're going to see whether grammar 2 and the English non-word are correlated. Okay, so how do we do that? We go to Stat, Basic Statistics, and then down all the way to Correlation. So let me repeat. You go to Stat, Basic Statistics, all the way down to Correlation. Now, here we are in Correlation, and what we're going to do then, we're going to enter the variables that we want to correlate. Now, in this case, we're going to correlate 2 variables. We're correlating grammar 2 and English non-word. Okay, that's all we need to do. So we click OK, and here we got a graph. Okay, we got a graph. Now the first thing that we can do with this graph is we can check whether we do have a linear relation. So how can we check? And it's obvious that we do have a linear relation, and on top of that we see that we have a positive linear relation, but we need to make sure. Okay, so what we do then, double click on the right, so we do a right click, and then we're going to add, and we're going to add a regression fit. So we add a regression fit, and we want a linear one, so remember that it has to be a linear relationship, so do linear, and boom, we get our line. Okay, so this pretty much solves our third assumption. We had to show that, the fourth assumption, that we had a linear relationship between the 2 variables. So this shows that we do have a linear relationship. Now here, notice that we don't see any red values here. So this is also suggesting that we don't really have any outliers here, which is the third assumption. So with this then, we have satisfied all four assumptions. We do have continuous variables, we have related pairs, we have absence of outliers, we don't see any red points, and we have a linear relationship. Those are our four assumptions that we have just checked. We need to check these assumptions whenever we run a correlation. Now, in this chart, notice that we also get here an R value. This is Pearson's R value, and in this case we have a 0.797, which is pretty much 0.8, which is very high. So we do have a very high correlation between Grammar 2 and English non-words. Okay, there's a very, very high correlation between the two. All right, so we click OK, and we send that back there. Now, if you need to print this and you need to include this in your report, remember you click here and you can send it to Word or PowerPoint or wherever you want. Okay, so this is the first chart that we get here. Let's go down and see what else we got here. We basically got here a correlation value that we already had. So we got a 0.797, and we see that we had 104 rows, so we have 104 values. We have a lot of data. Okay, so this is what we get then when we run a correlation. Now let's run what we call a simple regression. So in a simple regression, we're going to have two variables. Okay, so to do that, we're going to go to Stat, Regression, and we're going to go to Fitted Line Plot. Fitted Line Plot. So we go to Fitted Line Plot, and notice that we have here an entry for response and a predictor. Now remember that the response is whatever we are trying to predict. Okay, so we're trying to predict the value for Grammar 2. Okay, and what is our predictor? Our predictor is what we call here the X. Remember, this is going to go in a graph, and in this case we're trying to predict whether the English non-word value, the English non-word test, can predict a value for the Grammar 2. Okay, so we put that there, and we want a linear regression model. Okay, so we click OK, and this is the information that we're going to get. Okay, so we get here an R square, 63.45%. That's pretty good. So we can see that based on the English non-word test, we can predict 63.45% of the score on the grammar test. Now here we have an analysis of variance. Okay, we will come back and talk a little bit more about this when we do multiple regression, so we don't worry about this yet. We get our graph. Notice that we do have a straight line, so this satisfies the linearity assumption that we were checking. We also have here the R square value. Let me make this big so we can see that better. Okay, so we have the line that satisfies linearity. We have here the R square value. Okay, so this pretty much how much of the variation are we predicting with this model. And we have a formula. Okay, and that formula then has a constant, and then it has a value here that we need to multiply by the English non-word value, and we can predict then the value for Grammar 2. Okay, so again, if you need to print this, because here you also have the information for the R square, what you do then is you go back to the chart here and you click on the little line here, the little arrow, and you can send it to Word or you can send it to WordPerfect. Okay, and that's the way then that we run a correlation. We know how to read the data that we get from the analysis, and also how we run regression. But remember that before you do all that, you need to make sure that your assumptions are met. In this case, we have 4 assumptions for the correlation. When we start talking about the multiple regression in the next part of this program, we will learn that we have other assumptions that we need to check. Okay, now we can also run the regression with the assistant. So we go to assistant and then regression. Assistant, regression, and it's going to give us three options that we can choose from. We see that we can run a simple regression, that's what we're going to do, a multiple regression, and optimized response. Okay, we're going to use simple regression in this case. Again, just as before, it's going to let me pick or decide what is going to be my Y column. Now remember that the Y column is going to be the response. Okay, and in this case we wanted the response to be grammar 2, and is asking me for the X column. Now the X, remember, was the predictor. Okay, so we put here the predictor. Sometimes the Y column is called the dependent variable because the Y depends on the X, and the X is called the independent variable. Okay, so we have many names. So remember, the Y is the response, okay, or the dependent variable, and the X is the predictor or the independent variable. This is the one we use to predict. So X predicts Y. Remember that. X predicts Y. Okay, then this is asking us for the type of regression model that we want. We want a linear or quadratic. We will let the computer decide what the best model is going to be. Notice that when we run a regression, we could get a curved line like this, and that's okay. Okay, because that is still a line, and this is going to capture the best relation that we have between those two variables. Okay, so we let the program pick for us. So we click OK, and we get this chart that you saw before, and we should be able to read pretty much here without any problem. Notice that we get the chart with the regression line. We can see that this is it is possible to draw a line, and this line is going to then capture the minimal distance from the values to that point. We get the formula. Okay, so here we have the little formula, and this formula then is the one that is going to allow us to predict the value for Y. So Y, remember, is grammar 2, X is the English non-word. So if I know a value for English non-word, then I can predict what value I can get for grammar. Here at the bottom of the left hand side, we can see that we get a score for the correlation, and in this case we got 0.80, and we see that this is in the green area and it says perfect positive, so this is a very high correlation. Remember that correlations run from 0 to 1, 1 being a perfect correlation, so this is a pretty good correlation that we have here. In the middle graph, we get the value for R square, and in this case we can see that our R square is 63.45% as we got before, and this pretty much explains the variation in grammar 2 that can be explained by the regression model. Okay, so we predict 63.45% of the variation. And at the top we can see a little p-value there, and we can see that it says yes, so our score here is on yes, and it's basically telling us that the relationship between grammar 2 and English non-word is statistically significant, and we will learn how to read p-values later. Let's see what else we get when we look at this model. So we go down here, we see our chart again, and we see some points. So these are the red points that we need to check. If you click or you put the marker here on the red point, it tells you what row. So you should go back to your data. So here, for example, says row 4. So I go to my row 4, which is down here, and then I can see whether I actually entered the data wrong. Sometimes when we're entering data, we enter data wrong, so we need to double check those points. Here we get the same, remember, but now it goes horizontally. And again, we get some red points, so check those red points, make sure that the data was entered correctly. Then we get a confidence interval for our model, and we can see that pretty much everything falls within those blue lines, so that's pretty good. And then finally we get like the card report is called in Minitab, and here then it says the sample is large enough to obtain a precise estimate of the strength of the relationship. So it's telling us that we do have a relationship. It's warning us here about unusual data, so we should be careful with these pieces of data. We should go back to our data and make sure that we enter those pieces of data correctly. It's also checking for normality. This is going to be something very important when we check for when we do multiple regressions. So in this case, it's telling us that we don't need to worry about normality because we have a large number of data. Okay, so we don't need to worry about that. And then it gives us a little recommendation for the model fit. Okay, so here then you have reviewed how to run a regression, a correlation, and you learned how to do a simple regression. Simple regression, remember, is when you have two variables that you're trying to see how well one can predict the other. Okay, so now we're ready to go back to our PowerPoint and learn a little bit about multiple regression. Let's go. Okay, so now we are ready to start talking about multiple regression. However, I suggest that you stop the recording here and you go back to your data and rerun the correlation and regression for the French and O'Brien data that you have in today's lesson. That way you know how to do a simple regression. If you know how to do a simple regression, running a multiple regression is going to be very, very easy. Okay? Now, whenever we run a multiple regression, we need to make sure that we satisfy the following points. One, that we have normality of errors. We need to check that our errors are going to be distributed normally. We will see how we can test for this. Then you must check again that there is linearity. Then you must have independent observations. We will see what this means. And finally, there is this requirement of homoskedasticity or homoskedasticity, has two names, and here it means that you have to check whether you have equal error variance in your data. For normality, you're going to get these values, and I will show you how to get these values. Notice that there is a Ryan-Joyner value. This is the equivalent of the Shapiro-Wilk that we typically use in acquisition, and we get an accompanying p-value. So now it is time for you to learn what these p-values mean. Now, these p-values are associated with hypothesis testing. So whenever we have a hypothesis, we're always going to have what we call the null hypothesis, and we're going to have an alternative hypothesis. In this case, we are testing for normality of errors. We're making sure that our errors are normally distributed. So that's going to be our null hypothesis. It says errors are normally distributed. That's the null hypothesis. Now, the alternative hypothesis is the opposite. Errors are not normally distributed. And in this case, we're allowing for a margin of error of 0.05. 0.05. Okay, this is going to be the critical value in this case. Now, here we have the p-value and we have this alpha. So we're going to compare the p-value against this alpha. Now, how do we decide if this is a good p-value or this is not a good p-value? I'm going to give you a secret. Okay, so this is a secret formula. And it says, P is low, H null must go. P is high, H null can fly. In other words, it can stay. What does that mean? If your P is lower than your alpha, that means H null must go. You must reject the null hypothesis. Okay? And if P is high, higher than 0.05 in this case, that means that the null hypothesis can fly. In other words, it can stay. You do not reject it. Okay? So, if we get a p-value in this case that would be lower than 0.05, we have to reject the null hypothesis. And if we get a value of p that is higher than 0.05, then the null hypothesis goes. Okay? Now, remember that before, when we were doing correlation, I told you that you should check and see whether you had a p-value that was higher than 0.05, because we want the, in this case, the errors to be normally distributed. So in this case, notice that all of the values except for one, grammar 1, are normally distributed, and we have one that is not. Now, if you get one value, like in this case, that is not normally distributed, you can still run the analysis, but you have to point that out in your report. Okay? Here we're checking French and O'Brien. These are very famous people, and notice that they do have this problem with the set in grammar 1. Okay? So this is when we check for normality of errors. Now, in the case of normality of errors, notice that if you get a p-value higher than 0.05, is good, and that's because p high, null can fly. In other words, you're showing that the data are normally distributed. So that's assumption number 1. Assumption number 2, you have to check for linearity. Okay, I will teach you how to do this, and as you can see here, we're going to get many charts. So these are the different relations that we have between our variables or amongst our variables, and as you can see in all of them, I can pretty much draw a straight line. Okay, so this is the way that you check for linearity. Assumption number 3, you have to make sure that you have independent observations. Why is this, and what does it mean when we say that we need independent observations? Sometimes when we have variables, two variables might actually have a very high correlation. And if they have a high correlation in those two variables, this is going to be affecting the score that you're going to get for your regression. So this is why you have to make sure that you have independent observations. Now, how do we do that? Well, when you do a multiple correlation, and I will show you how to do this, you will get these values. Now remember, correlations are usually evaluated on a scale from 0 to 1. Now in this case, and again, this is a problem for French and O'Brien, we can see that here we have a very high correlation. Finally, we need to check for almost elasticity. Remember, this is going to be that we have equal variances. So when we check for this, again, we're going to do this with hypothesis testing. So the null hypothesis is going to be that variances are equal. The alternative hypothesis is going to be that variances are not equal, and we're allowing alpha to be 0.05. This is typically what we do in language acquisition. Again, remember our song, P is low, H null must go, P is high, H null can fly. We run the test, and this is what we call Levine's test. So we will learn how to run Levine's test, and notice that in this case we got a 0.000. Okay, now in this case P is low, H null must go. So what does this mean? This means that French and O'Brien did not check for variances being equal, almost elasticity, and in this case notice that the variances are not equal. And we can show that, in fact, when we graph the different variances. You can see here you have Levine's test here, and it says 0, 0, 0, so that means this is not, the variances are not equal, and you can see here in the chart that actually the variances are not equal. Some variances here are very small, and some variances here are very large. Okay, so here again we do not have equal variances. Okay, so this is a test for equal variances. Again, if you have this problem, make sure you report it, otherwise other researchers are going to catch you and notice this for your analysis. Okay, so now we are going to then learn to check the assumptions, these 4 assumptions that we discussed. So let's go to Minitab. Okay, so now we're back in Minitab, and now then we're going to check for our assumptions. The first one is normality of errors. So to check that, basically we go to Stat, Basic Statistics, and then we go down all the way to Normality. So Stat, Basic Statistics, Normality. And then here we're going to then check all these variables one by one. So in this case, let's check grammar 2 first. So I'm going to put grammar 2. Now remember that here you have three options. You have Anderson-Darling, Ryer-Joyner, which is similar to the Shapiro-Wilk. This is what we want. And we have the Kolmogorov-Smirnov. We don't use that. Typically we use the Ryer-Joyner, which is similar to Shapiro-Wilk. Okay, so we want that. And we will check whether this is then normally distributed or not, the errors. We do that, and then notice that we get a straight line, and we get all the points pretty much sticking to that line. However, remember that our eye is not good enough. We need to look at here, okay? So here we have the Ryer-Joyner value, which is the Shapiro-Wilking test. And in this case, notice that it says that we got a p-value higher than 0.1. Now, in this case, remember, for normality, we need to get higher than 0.05. In this case, we have higher than 0.05. So notice that here, then, we conclude that grammar 2, the errors in grammar 2 are actually normally distributed, okay, which is what we want. Let's check. So you need to check for all your variables. Okay, so here I'm just going to check for a couple of them. So let's check what happens with grammar 1. Grammar 1, again, we're going to do the Ryer-Joyner, Shapiro-Wilk, and we click OK. And notice that now our chart does not look that beautiful. You see, we have lots of points going in and out. In this case, the Ryer-Joyner test is 0.967, and we have a value of less than 0.01. Remember, for the data to pass the test, you need to have a p-value higher than 0.05. This case is lower than 0.05, so this one does not pass the normality test. Again, make sure you note that in your paper. So you need to do this for all the variables that you have in your experiment. Check for normality. Okay, so now we're ready to check for linearity, and we're going to be checking for linearity and independence of observations, okay, together. Now the way to do that, we go to Stat again, Basic Statistics, so Stat, Basic Statistics, and we're going to go down to Correlation, okay, because we're going to see whether the variables are actually correlated or not. Okay, so we go to there. Now here then, we are going to enter all our variables because we want to see if there's any correlation amongst them. Okay, so we enter all our variables here and we just click OK. So enter all the variables and click OK, and you're gonna get this terrible chart here with all the correlations. Okay, so this pretty much shows the correlation between grammar 1 and grammar 2, intelligence and grammar 2, and then of course you want to see if these relations are going to be linear or not. So to do that, double click, and then you're going to add a regression fit. We add a regression fit, and we want linear, and there we go. We can see that we can get pretty much a straight line in all of them. Okay, so notice then that that is pretty much the way that we can prove that our data are going to be linear. Okay, now with that correlation that we did there, if we go down a little bit, we're going to get a little chart here, and in this little chart we're going to see whether our variables are independent or not. They will be independent if they're not highly correlated. Now remember, correlation, the maximum value that you can get is a 1. So if you have any value that pretty much is higher than 0.75, then you should be a little worried about that. Okay, so in this case, notice that we have the correlation between grammar 2 and the Arabic non-word. It's a high correlation. Here we have the grammar 2 and the English non-word. We have a 7.9. That's also pretty high. These are okay. Here we have a 0.093. That's okay. And here we have a 0.948. That's not okay. Okay. So notice that this is almost perfect correlation. In fact, remember that 1 is the maximum. So notice that in this case, then, we do have 3 very high correlations. Okay, so when you have 3 high correlations, that's not good. Okay, so you need to report that some of those variables are actually correlated and they're not independent of each other. Okay, now we're ready then to test the fourth and last assumption, and this is going to be the assumption for homoskedasticity. Now the way to check this, we're going to go to stat again, stat. We're going to go now to ANOVA. Okay, so stat ANOVA, and we will have a whole lesson on ANOVA later. But here we're going to go from ANOVA down to test for equal variances. Remember that homoskedasticity basically checks to see whether we have equal variances. So here we're going to apply the test for equal variances. So click OK. And then here, what you're going to do then is, in the upper box here, you are going to make sure that you have response data are in a separate column for each factor level. Okay, and you're going to enter again all your variables. Okay, so enter all your variables here. Okay, and click OK. So I repeat, you're going to go to stat ANOVA and then test for equal variances, and you enter all your variables, and make sure here you have response data are in separate column for each factor level. Okay, so click OK, and notice that here it says method, so it's actually applying again hypothesis testing, and the hypothesis then, the null hypothesis in this case, is that variances are equal. The alternative hypothesis is that at least one variance is different. Okay, so it's going to check whether the variances are all equal or not, and then it gives you a significance level, and this is the one that we normally use. We use 0.05. Then it gives you the Bonferroni confidence intervals. We don't worry too much about those. And here we are interested in Levene's score. So for Levene, we got a 0.00. Remember, P is low, then null must go. So in this case, we have shown through Levene's test that the variances are not equal. And then the program gives us a little chart, and with that little chart, notice that we can see that in fact the variances are not equal. Okay, this one is a small variance, while this is a very large variance. So notice then that here again we have a problem with homoskedasticity, and again that needs to be reported. Okay, so now then you have learned how to check for the 4 assumptions that you need for multiple regression. One is normality, the other one is linearity, independence of observation, and then finally homoskedasticity. Okay, after you've checked your 4 assumptions, you're ready to run the multiple regression test, and that's what we're going to do next. Let's go. Now we're going to learn how to run a hierarchical multiple regression. And we say hierarchical because we have to enter the variables in the order that we want them to be considered as we deem them more important in the analysis. To do this, we go to stat, regression, regression fit. I will show you this in Minitab later. Then we go to stepwise, and stepwise you're going to go stepwise E include, and then results you want to have an expanded table. I will show you how to do this in Minitab later. When we run the hierarchical multiple regression, we're going to get a regression equation. And in this regression equation, you can see what each of the variables is adding to the value of my grammar 2. We will also get a chart. And in this chart, I will mention what columns are the important columns. One is the coefficient. Notice that this one summarizes the coefficients that we find in the equation. For example, here we have the constant is 13.65. That's the constant that we have in the equation. The contribution for grammar 1, we see that it's 0.0446, and that's exactly what we have here, 0.0446, and so on. So this list of coefficients here basically tells you what factor they contribute to the equation. The other value that is important and should be reported is the value of the confidence interval. So this is how much my values in the equation can vary. So for example, for the grammar, we saw that the coefficient was 0.0446, but if we add this confidence interval, then it could actually vary from all the way from minus 0.1089 to 0.1981. Okay, that's how much variation it can exhibit. There's another column that is important, and this is the column with the p-values. And again, a p-value means that we have done, in this case, a t-test. We will talk about t-tests in the future, but then we should be able to understand these values. So let's see exactly what we mean by these p-values here. Now, in this case, the null hypothesis is that the coefficient is equal to 0, and the null hypothesis is that the coefficient is not equal to 0, and again, I'm measuring this at an alpha of 0.01. Now, we do not want the coefficients to be equal to 0. We want the coefficients to be contributing something, okay? And this is what this test is trying to show us. Again, remember, P is low, H null must go, P is high, H null can fly. We run the test, and notice then that we got those values for p-values. Now, notice that in this case, we have a 0 for the constant. So that means that this is definitely not equal to 0. Okay, remember, P low, null must go. So P is low, it means in this case I reject the fact that the hypothesis that the coefficient is equal to 0. And that's my constant. Notice that I get another 0.001, lower than 0.05, with the Arabic non-word test. So these are the values that are different from 0. Okay, the values that they're contributing, the coefficients. Okay, so the coefficient here, we can see that this is 13.65 for the constant and 0.0546 for the others. So those are the ones that are significantly different from 0. We are also going to be getting what is called a model summary, and here we're going to be getting an R-square value. So here we're getting a 68.78%, which is what, if we consider all the variables, if we include all those variables in the order that I specified, then I can explain 68.78% of the data. Then we will also get an analysis of variance. And again, here what is important is this contribution column. This tells me how much each of the variables contributes to that final R-square that I got there. So in this case, notice the regression itself is 68.78%. This is the value for R-square. Then we have the value for grammar 1 is 30.21%, and then the value for the Arabic non-word test is 36.29%. Those are the ones that contribute the most to the equation that we have there. So now let's go to Minitab and let's run the regression for our data. So to run a regression, we're going to go to Stat, Regression, and then we're going to go Regression. So Stat, Regression, Regression, and then we do Fit. Okay, so now here where it says responses, we're going to enter our response. In this case, our response is grammar 2. We enter grammar 2 for the response. Okay, and then for the continuous predictors, we are going to enter all the other variables. Okay, so we're going to have grammar 1, intelligence, L2 contact, Arabic non-word, and English non-word. Okay? Now, we are going to go to stepwise, and in stepwise, we're going to make sure that we have stepwise. Okay? So you're probably going to find yours in none. So here you click and you go to stepwise. Okay? And you have all your variables there. Then you have to make sure that we include those variables in our system. So what you're going to do is you're going to click, and then with control, you're going to make them all blue. Okay? You make them all blue like that. And then you tap here on E, so that you include every term in the model. Okay? So then all the variables then should have an E. That means that we're going to include them in every model. So make sure you do that so that we do run hierarchical analysis. Okay? Then we're going to go to results, and then here make sure the default here is basic tables. Okay? Make sure then that you go to expanded tables so that you can get all the information that you will need. So expanded tables, and here everything should be accepted with the exception of the Darwin-Watson statistics. Okay, so everything should be checked except Darwin-Watson. Okay, click OK. So now I think we're ready to run the regression. Let's run it. Okay, so it takes a little while, and boom, it appeared there. Okay, so what do we get here? Well, we're going to get an R-square. Notice that we're getting an R-square of 68.78. Remember this number because later we're going to run a different type of regression, and we're actually going to get a higher result. Okay, so I'm going to show you how to run a different type later. So here we get 68.78% R-squared, which is not bad. Then we get our equation, as we said before. So here we have the equation. Now with this equation then, notice that we have different factors for each of the variables. We are able to predict then the value of grammar 2. Then we get our list of coefficients. So here the second item here in the columns is going to be the coefficients. These are the coefficients that appear in the formula, as we mentioned before. Then we have here the confidence interval for those coefficients. That should be reported. If someone decides to run the experiment again, notice that it's very unlikely that they're going to get exactly the same values. But if you give the confidence interval for your data and the results fall within that 95%, then notice that pretty much they confirm your results. And then here we have the t-test. We will talk about t-tests next time. And we have the p-values. Now remember that here, basically the hypothesis is that the value that we get for the coefficient is significantly different from 0. Okay, so we get 2 here that are below 0.05. One is the constant, and we can see that it's 1365, so that's significantly different from 0. And we get the Arabic non-word test, and we can see that that one is a 0.001. Okay, so those are the two. The others, they have a high p-value, p high, h0 must fly. So notice that in this case means that the null hypothesis, in this case, is that the coefficients are equal to 0. Then notice that they are pretty much negligible in that sense. Then you have the model summary. Again, you have the R-square and some other values. We ignore them for the moment. You have the analysis of variance. This will become more important when we start talking about ANOVA. But in this case, again, notice that the p-values that we saw before are repeated. Okay, this is what's going to be important here. Okay, so this means that these two, regression and the Arabic non-word test, those are the ones that are going to really influence the variance that we're going to find in our data. There is one more piece of information here that is interesting and should be reported, and this is the contribution column here. Here we can see how much each of the variables is contributing to the model. So we see that the regression, this is our R-square, is a 68.78%. Grammar is contributing a 30.29%. The second one is going to be the Arabic non-word test with a 36.29%, and the others are contributing minimally to the variation that we are trying to explain. Okay, fits, this gives me an idea of the elements, and here you can see it says observation. This is what row number. These data might be problematic, so it's a good idea to go back and check those data. And then we have a Pareto that we don't need to worry about. Okay, so then this is the way that you would run hierarchical analysis. Okay, now the important thing to remember here is that we got an R-square of 68.78. So we must remember that number, 68.78. Now the program also has the assistant, and then with the assistant we can also run the regression. So we go to Assistant, Regression, and click on Regression, and as before, this is going to give us three alternatives. We're going to have a simple regression, a multiple regression, and optimize response. Okay, so this is going to find the best model. Okay, so for example, if a variable does not contribute much, or if a variable pretty much is correlated with another variable, then the system is just going to take one variable. So let's run a multiple regression. You can repeat the exercise if you want at home with the optimized response to see if you get many times you're going to be getting the same response. Okay, so here basically it's asking you for the same information that you had before. Okay, so it's saying, okay, what is the response variable? Well, our response is going to be grammar 2. And what are the continuous variables? Remember that that was one of the conditions to run a regression test. Then we have grammar 1, intelligence, L2 contact, the Arabic non-word, and the English non-word. Okay, and then we click OK. And this is going to run the best regression analysis that the computer can find. Okay, now let's see what the computer found. Remember, before we had a 68.78. Now, you see, running a different analysis, we see that now we have a 72.82. So that means that there's a better formula than the one we had found before. Remember, before we ran a hierarchical test, so we forced the program to consider the variables in that order. Okay, now if we let the computer decide which are the relevant variables, then the computer does it differently. Now in this case, notice then that we got an R-square of 72.82, so this is a better result. Okay, so it depends on what you want to do with your test. If you are trying to, for example, repeat an experiment, then you have to follow the same order that was followed before. But if you're doing your own experiment and you want to find the best result for your data, then you might as well let the computer do it. Now, notice here then it says that the relationship between y and x in the model is statistically significant. Okay, so we do have a significant variant. Now, notice here is going to give us some graphs, and in these graphs, notice that one graph here has been left gray. Okay, so that means that the L2 contact variable is not going to be taken into account for the final formula. All the others are going to be taken into account with the exception of the L2 contact. Okay, it found a better formula that way. Okay, so let's see what that formula is going to be. Let's go down. Okay, so I repeat here then we have the information whether this is a statistically significant relationship. We have the R-squared value. We can see what variables are going to be considered. These graphs here you can ignore. Now here again is going to give you some values that you should go back and check, and if not, just report them. And then here we have the formula. It's a little tiny, but you can see that this formula is very different from the formula that we had before. Okay, so here it says x1 is grammar 1, so basically we're going to have a constant, a different constant, and then 0.446, that's the same one that we had before, multiplied multiplied by grammar 1. Then we have another variable here, the factor multiplied by intelligence, And as you can see, this one is a lot more complicated than the one before. However, it gives us a better R-square, and that's what we are after. Here you can see the impact of the variables. You can see that definitely the Arabic non-word test is the one that is impacting the most our result. And that's exactly what French and O'Brien were trying to prove. Remember that they were trying to prove whether phonological memory had an effect on the grammar, okay? And then in this case, they discovered that yes, okay, phonological memory is definitely going to be influencing your score when you do grammar. So if we keep on going down, then you're going to get your report card, and then it says the sample is large enough to obtain precise estimate of the strength of the relationship. So we know that there's going to be a statistically significant relationship between all those variables. It warns us about the unusual point, so we should go back and check. Notice that before we did find a problem with normality, but notice what it says here. It says because you have at least 15 data points, normality is not an issue. Okay, so if you have a large set of data, then normality does not become an issue, right? So notice that there are two ways then that you can run your regression. There are actually more ways, and you can explore that on your own, but these are the most common. So one is going to be the hierarchical, and this is the one where you're going to then decide what order you're going to enter and measure the variables. And the other one is just let the computer do it, and this is what we might call a normal regression. So the computer finds pretty much the best combinations, the best subsets of variables, and then you can run that. Okay? So now you know then how to run multiple regression. The last item to discuss in our program today is the way that we're going to report our findings. So this is the way then that we will report what we did. I'm going to read through this and then I will explain what parts we have here. A hierarchical linear regression was calculated to predict the value of a time 2 grammar test based on the scores of a time 1 grammar test, an intelligence test, a language contact test, an Arabic non-word phonological memory test, and an English non-word phonological memory test. A significant regression equation was found, blah blah, and we list there the equation. This model yielded an R-square of 68.78%. The different variables contributed the following value to our final equation. We list the values. The significant predictors were the Arabic non-word test and the time 1 grammar test. So notice here that we really have 6 different parts. The first part, we basically say what kind of regression we ran. Now in this program we discussed 2 types of regressions. We learned how to do a hierarchical linear regression, and this is what we are reporting here, and we also learned how to do a standard regression. Then we say what our predictors were, and of course what item we were trying to predict our response. So in this case our time 2 grammar was our response, and we had a whole bunch of predictors there. We list them all. Then we list the equation that we found, or that the program found. Then we report the R-square value for our model, and then we discuss the value that the different variables contributed, and from those variables, also reading their p-values, we report what the significant predictors were for our particular research. So this is the way then that we would report our research. In addition to this report, you would also include the charts, and ideally your charts should include the important information that we discussed before. Very important when you present your charts is that you include the confidence intervals, in this case for the particular coefficients. If someone is going to replicate your study, they're never going to get the exact same values. However, if their values come within the range of the confidence interval that you have determined, then we can say that your study has been successfully replicated. Okay, time has come now for us to discuss our projects for next week. Before you do the project, I would recommend that you try to repeat what we did in the lesson using the data in French and O'Brien. Try to repeat the correlation test, try to repeat the simple regression, and then the two kinds of multiple regressions that we did in the test. After that, I recommend that you move on to the project for next week. Now, the project is based on an article by Larson Hall, 2008. The article is called Weighing the Benefits of Studying a Foreign Language at a Younger Standard Age in a Minimal Input Situation. This appeared in Second Language Research 24, pages 35 to 63. In this study, she was analyzing the behavior of Japanese learners of English, and these are kids that began a formal study of English outside school at an age younger than 12. So the research question that you're going to explore is this: are number of hours, aptitude, and scores on a phonemic task useful predictors of scores on a grammaticality judgment test? Are number of hours, aptitude, and scores on a phonemic task useful predictors of scores on a grammaticality judgment test? Okay, so what are you going to do with these data? And here I have divided them into two parts, so maybe we should take 2 weeks to actually complete this project. The first project relates to correlation and single regression, and then the second one refers back to hierarchical regression and standard multiple regression. So you should go back and listen to the first part of the video and then do the project, and then the second part of the video and do the project for the following week. So this video is going to keep you busy for 2 weeks. So the first task then is to perform a single correlation study between the number of hours of input and grammaticality judgment test. You will need to check the basic assumptions for correlation, and you will write a report with your findings. And the second part, you will perform a single regression using the data in task 1, and again report your results. Okay, so this is pretty much the first part of the video, and I recommend 1 week for that. Then for the following week, I would recommend then the second part, which is perform a hierarchical regression with the scores of the grammaticality judgment test as the response and the other variables as the predictors. Check the basic assumptions and then report the assumptions and the results of your hierarchical regression. And then, just as we did on the video, run a standard multiple regression using the assistant and report your results and see if you get a different and a better result. Okay, so I recommend that for this one then we actually take 2 weeks. The first week of correlation and single regression, and the second one hierarchical regression and a standard multiple regression. And that's it. That brings us to the end of lesson 4, where we discussed simple regression and multiple regression. This video has a lot of information, a lot of new information, important information, so I recommend that you watch it as many times as you need to, and let's take 2 weeks to actually go through this video and the projects. Have a good next couple of weeks. Okay, so now we're back in Minitab, and now then we're going to check for our assumptions. The first one is normality of errors. So to check that, basically we go to Stat, Basic Statistics, and then we go down all the way to Normality. So Stat, Basic Statistics, Normality. And then here we're going to then check all these variables one by one. So in this case, let's check grammar 2 first. So I'm going to put grammar 2. Now remember that here you have three options. You have Anderson-Darling, Ryer-Joyner, which is similar to the Shapiro-Wilk. This is what we want. And we have the Kolmogorov-Smirnov. We don't use that. Typically we use the Ryan-Joyner, which is similar to Shapiro-Wilk. Okay, so we want that. And we will check whether this is then normally distributed or not, the errors. We do that, and then notice that we get a straight line, and we get all the points pretty much sticking to that line. However, remember that our eye is not good enough. We need to look at here, okay? So here we have the Ryan-Joyner value, which is the Shapiro-Wilking test. And in this case, notice that it says that we got a p-value higher than 0.1. Now, in this case, remember, for normality, we need to get higher than 0.05. In this case, we have higher than 0.05. So notice that here, then, we conclude that grammar 2, the errors in grammar 2 are actually normally distributed, okay, which is what we want. Let's check. So you need to check for all your variables. Okay, so here I'm just going to check for a couple of them. So let's check what happens with grammar 1. Grammar 1, again, we're going to do the Ryan-Joyner, Shapiro-Wilk, and we click OK. And notice that now our chart does not look that beautiful. You see, we have lots of points going in and out. In this case, the Ryan-Joyner test is 0.967, and we have a value of less than 0.01. Remember, for the data to pass the test, you need to have a p-value higher than 0.05. This case is lower than 0.05, so this one does not pass the normality test. Again, make sure you note that in your paper. So you need to do this for all the variables that you have in your experiment. Check for normality.